Before we can talk more about how weird electrons are, we need to learn a little bit of physics and talk about light. And what is light and how does it behave? So light is a form of electromagnetic radiation. And I know we hear the word radiation and we're going, dangerous. Well, some forms of radiation are dangerous and others are not, right? So electromagnetic means that it has an electric field and a magnetic field, and those are oscillating. They're going up and down, getting stronger and weaker. So electric field is where an electrically charged particle would experience a force. Magnetic field is where a magnetized particle would experience a force. All electromagnetic waves move through space at the same constant speed, and that is called the speed of light. It's 3 times 10 to the 8th meters per second. And you see a number like that, and you're like, I don't know. That's 186,000 miles per second, which is fast enough to circle the Earth 7 times in 1 second. It's crazy fast. Really, really fast. So this is one way of sort of visualizing electromagnetic radiation. You have the electric field component, and perpendicular to that, you have the magnetic field component. And they're traveling along through space at the speed of light. Light travels faster than sound. So here we have a picture of lightnings. Looks like it's striking that building over there. So we know from life experience, you see the lightning and then you hear the thunder later. They happened at the same time. The reason we perceive them at different times is because sound only moves at about 340 meters per second, and light is moving at 3 times 10 to the 8th meters per second. So the light gets to us much sooner than the sound. And yes, you can actually estimate how far away the lightning strike was by measuring the distance, the amount of time between when you see it and when you hear it. Some characteristics of waves or parameters that can be measured: the amplitude. That's how tall the wave is. So if you draw the wave like this, going up and down and up and down, and here's like the midpoint. The amplitude is how tall a peak is or how low a trough is. Amplitude is related to the intensity of the light. So larger amplitude, brighter light. What we're more interested in for chemistry is the wavelength, which is the length of the wave from one crest to the next crest. And that's given the Greek letter lambda. So lambda is the length of the wave. With visible light, different wavelengths are perceived by our eyes as being different colors. So red light has a longer wavelength, and blue light has a shorter wavelength. Yellow light would be somewhere in between. And that's a whole nother fascinating area of study, human vision. Wow. Different amplitudes, again, are going to be different brightness. This would be dim light, and this would be bright light. Another thing we can measure is the frequency, and this has a symbol nu. I know that looks like a V. It's not a V. It's the Greek letter nu, which is kind of like a V that's a little curvy on one side. Looks an awful lot like V for velocity, but it's not. Again, that's not something I'm going to try to trick you on. So this is the number of waves that would pass a given point in a period of time. So usually that's a second. So the number of waves would be considered the number of cycles, and so the units are hertz or cycles per second. How many waves pass in a second? That's the frequency. The total energy of the wave is proportional to its amplitude and to its frequency. And that kind of makes sense if you think about going to the beach. Maybe we'll go over to Pismo, and you're standing on the beach, right? And the waves are rolling in. And you're standing, where they're hitting you, but you're not in over your head. And so the wave comes and it hits you. Well, if these are big waves, that might knock you over, right? It has more energy. It can knock you flat. More energy because the wave is taller. It has a higher amplitude. But also, even if they're the same amplitude, if they're more frequent, you're getting hit bang, 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 instead of just bang, bang. And you get time to recover in between. These guys are hitting you so fast, that might also knock you over. There's more total force there. Does that make sense? When waves are traveling at the same speed, which electromagnetic radiation is, the shorter the wavelength, the more frequently they pass. So let's draw more ugly pictures of waves. So if we imagine these waves, traveling in this direction, and here you are over here, and you're going to count the waves that pass you. If these are traveling at the same speed, right, you're going to see more peaks from this one than from this one because of the frequency. So if the frequency is higher, that means the wavelength is shorter. Longer frequency is lower. I said that wrong. Longer wavelength is lower frequency. So they are inversely related by the speed of light. The color is determined by the wavelength, which is related to the frequency. So you can say it's determined by the frequency or it's determined by the wavelength. Same thing. What we call white light is a mixture of all the colors of visible light. Here we have a picture of a prism, and we have white light hitting the prism. And as the different wavelengths of light get bent by this interface, they bend at different angles. And so we pass it through here, they separate a little, and we pass it through another one, and they separate more, and we see it separate out into a rainbow. And this is the same effect that happens when you see a rainbow in the sky. Or we used to have a light fixture that had some cut glass pieces, and in the afternoon when the sun would hit it, it'd make little rainbows all over the room, right? Same thing. The colors that are present are red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. That's how I learned them, just to think of it as a name, right? Roy, G is his middle initial, and Biv is his last name, so Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Sometimes when you see pictures of rainbows that people have drawn, especially children, you look at the rainbow and you're like, that doesn't look right. And you can't put your finger on it, but they've got the colors in the wrong order. Drives me nuts. So this is the correct order, right? If you go purple and yellow and blue and green, it's wrong. That's not how rainbows are, right? You can draw them that way, but it's not how they are. So how is it that we see things as different colors? It has to do with which frequencies, which wavelengths of light are absorbed by a substance and which are reflected. So here, this woman is wearing a red shirt. So as white light containing all the frequencies of light come in and hit her shirt, a lot of them are absorbed and the red ones are reflected. And so what we see, like there's a red backpack, right? So the red light is coming to my eyes, and so I see that as red. Right? The counter, the bench top, is black. That's absorbing almost all of the light, which is why black animals are so hard to take a picture of, right? Because they end up just looking like a solid black blob unless you really, really work at it, right? They're just absorbing all of the light. Any questions? Okay, so let's do a calculation. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So we're given one number, 515 nanometers, and one task, calculate the frequency. So 515 nanometers is the wavelength. What's the symbol for wavelength? The broken TP, yeah, lambda, the upside down lowercase y, or broken TP. I like that. So this is a calculation that needs an equation. And so we saw this equation. The frequency is equal to the speed of light divided by the wavelength. And the speed of light is 3.00 times 10 to the 8th meters per second. So we can plug that in here. And we're going to divide by the wavelength, 515 nanometers. Now, a lot of you are still not writing your units on your worksheets or your lab reports. And you would just write 3 times 10 to the 8th divided by 515, and you'd do the calculation and you'd get the answer wrong because you didn't look at the units. Please write the units. I put all the units in, and then I look at them before I calculate. This is meters, and that's nanometers. Those are not going to cooperate with each other. I need to have this bottom one be in meters. And the really quick and easy way to do this is to say, well, n represents times 10 to the minus 9, right? So instead of writing that little prefix, I'm going to write what it represents, which is times 10 to the minus 9, and there's the meter still. So this part is the nano. Okay? Now I've seen people trying to do this going the other way, going from meters to nanometers. It doesn't work that direction, sorry. So here we get 3 times 10 to the 8th, 3e8 divided by 515 e negative 9. And I'll write it down here because there's just so many numbers. This is what my calculator shows me. Nobody saw that good. I almost dropped my iPad. We're used to looking at the first several digits, right? And so, it's like, well, okay, we've got 3 sig figs on everything, so we'll call this 5.83. But what's at the end of this? Times 10 to the 14th. That cannot be overlooked. So always look at the whole number. That's times 10 to the 14th. That makes that from a nice small number, 5, that's a friendly little number, to this huge, ginormous number. I don't even know how quintillions or sextillions or whatever that would be. Really, really huge. And my meters cancel my meters. Sorry about those other scribbles. And so this would be, you could write it like that, per second. You could write it as second to the minus 1. Or you can say 5.83 times 10 to the 14th hertz, HC. Any questions? So visible light is electromagnetic radiation, but it's only a very tiny part of all the electromagnetic radiation. Shorter wavelengths, which are higher frequency, have higher energy. And so some of this is higher in energy than visible light, and some is lower in energy. So radio waves are the lowest energy, and gamma rays are the highest energy. High energy radiation can damage biological molecules. One of the ways it does this is by ionizing it. So it takes molecules and makes them into ions, which then really messes up the chemical reactions that are occurring in your body. So this is one way to represent the electromagnetic spectrum. So here is one scale showing the frequency in hertz. So this would be 10,000 hertz. Over here, 10 to the 24th hertz. We can also look at this in terms of wavelength. So this is small frequency, large frequency. This is large wavelength to small wavelength. They're inversely related. So this would be a very long wavelength. Like here, the wavelength here is 1,000 meters. That's just like really big, right? It's 1,000 meters, 1,000 of those meter sticks between one peak to the next peak. That's really long. And that is roughly the wavelength of AM radio signals. Really, really, really long. And here in the middle, we have the names of these different types of electromagnetic radiation. There's low energy on this end and high energy on this end. So we've got radio waves, microwaves, infrared. The visible light is just this little tiny section in the middle. Then there's ultraviolet, X-ray, and gamma. So this part, this little tiny section, is one of the parts that we're most interested in because we can actually see that. And so what they've done in this diagram is they've blown that up so that we can see the pretty rainbow, right? And here they're giving us the wavelength in nanometers. This was in meters. Here it's in nanometers. And so visible light ranges from about 400 nanometers up to 750 nanometers. But 750 nanometers does not correspond to 10 to the 5th meters or 10 to the 3rd for frequency, right? Because this belongs way over there, okay? Mentioned this before, we can use a prism to separate light by its wavelength. Here the light's coming in from the right side and it's bouncing off these surfaces and getting separated into. This is a continuous spectrum, we call a rainbow. And we'll see that if you get light from some other sources, you don't get a rainbow, you get a series of lines, and that's pretty significant. Infrared light, you recognize that person? That's me, and that's my daughter. She's 17 now. I think she was like 9. This is NASA's Jet Propulsion Laboratory. We got to go on a field trip, and they had this infrared camera. And so you could see yourself in infrared and in visible light. So infrared is can be used as like night vision, so you can see in the dark. It's not really that you can see in the dark, but you can make things out in the dark. Our eyes can't detect infrared, but we can develop electronic sensors that develop infrared and turn those signals into pictures. And so here, this orange color is representing a warmer temperature, and the blue in the background is representing a colder temperature. And you can see my phone was pretty warm there because I was taking a lot of pictures, right? Gamma rays are used to treat cancer. During radiation therapy, they target the tumor from multiple different directions. And the reason for this is when you shoot radiation through tissue, it not only damages the tumor that you're aiming it at, it also damages all the healthy tissue that it goes through. If you have a brain tumor, they might not be able to remove it because the process of removing it would do more harm than leaving it alone. But if we take radiation and shoot it at the tumor from multiple directions, this is only showing 3, it would go lots and lots of different directions in 360. You can cause a little bit of damage to the healthy tissue, but the tumor gets hit every time, and so the tumor sustains a lot of damage. So, you will get sick from radiation therapy, but it's not going to kill you, right? Hopefully it'll kill the tumor. And well, I guess I went through this. So there's some other types of radiation. I think I mentioned them down here. Microwaves, I did talk about infrared a little bit. Visible light, ultraviolet, X-rays. There's little sections, just like paragraphs in your book. You should definitely read those. I'm not going to talk about them. Waves can interact with each other, and this is called interference. We can have constructive interference or destructive interference. These two waves are said to be in phase, meaning they're lined up with each other. This peak and this peak, this trough and this trough, they're lined up with each other. And so when these interact, they build on each other. They add to each other, and it gets bigger, and called building construction, right? So we're building something. This is constructive interference. If the waves are out of phase, here the peak is lined up with the trough. When those add together, we have positive adding to negative, and they cancel each other out. And we call that destructive interference. And this is the idea that's used in noise-canceling headphones. Like your AirPods, the noise-canceling feature. You ever wonder, how do they do that? Just make all that sound disappear, but I can still hear the music? It's kind of crazy, huh? It takes the sound coming in and it shifts the wavelength of it. It shifts it so it's out of phase and plays it to you through the headphones. And so the noise coming in that's live and the noise that it shifted, they cancel each other out, and boom, it's gone. Crazy. Pretty cool. So we'll pick up with this on Wednesday.